είμαστε και live στο YouTube, να ξέρετε. Σε λίγο. Σε λίγα δευτερόλεπτα.
Υπάρχει αυτό, πες το στη Μίλκα.
Το ξέρουμε. Χθες το κάναμε τεστ με την Ελένη. Και επίσης, όταν δεν μιλάτε, να κάνετε mute το μικρόφωνο και την κάμερά σας. Έχει ένα lag. Έτσι, αυτό βλέπει και ο άλλος. Και τώρα είμαστε και live και στο YouTube.
Θα μου δώσει το τέλος εδώ. Εδώ θα μου το δώσει.
Όχι, θα μου λες εμένα. Αν μπορείς να φέρεις αυτό.
Όχι, καλύτερα να έχω αυτό. Για να το ελέγχω.
Το κάνω λίγο το λάμπο πιο πίσω. Και βάζουμε το βίντεο. Live. Στο YouTube. Εσύ γιατί να μην φαίνεσαι. Έλα εδώ. Χαρή. Σε πάω. Ναι.
Αυτά καταγράφονται τώρα.
Ναι. Εκεί θα μπουν, δεν καταγράφουν. Ναι, το ξέρω. Ναι.
Good morning, everybody. Can you hear me?
Yes.
Okay, thank you. I would like to thank you for your kind attendance, and I hope our webinar to be informative and useful with respect to your needs and interests. This workshop aims to inform the communities of scientists and decision makers acting in the fields of health and epidemics. It demonstrates through selected use cases the value of the European innovation in Earth observation and artificial intelligence and modeling for the development of a robust solution to combat mosquito-borne diseases and specifically the West Nile virus outbreak. The webinar comprises of 4 presentations. It highlights validated actions for short to mid-term forecasting of human cases and mosquito populations at various geographic scales in Europe. The first presentation concerns an overview of the whole activity and the concept behind it. In the following, my colleagues from the National Observatory of Athens, as well as our partners, Ecodev SA and University of Patras from Greece, will highlight the modeling and operational aspects of the developed solution as in the agenda here presented in the screen. Finally, yet importantly, I would kindly ask you to keep your questions for the Q&A session, which will take place after the presentations. Also, during the presentations, you can use the Q&A facility of the Zoom platform to submit your questions. We will collect the questions and we will try to reply to them during the webinar. Let also inform you that this webinar is recorded and it is presented live in the YouTube. So now I'll pass to the first presentation. I'm the first speaker of the day. So let me just tell you that this action is the outcome of the volunteer activity that it is conducted by a European group of partners in the framework of the EuroGeo Action Group for Epidemics. The Center of Earth Observation Research and Satellite Remote Sensing Beyond of the National Observatory of Athens is the research unit that has the mandate to conduct innovative research in the fields of Earth observation, data science, big data modeling and assimilation, environmental and emergency management. We play the role of the coordinator of this action group. We have been addressing societal priorities and we are delivering services that are beneficial in different domains, emphasizing mostly in risk reduction, civil protection, societal resilience, health, adaptation to climate change, energy, food security, and environmental protection. For those who are familiar with the intergovernmental organization GEO, I would like to mention here that this activity is part of the EuroGeo Action Group, Earth Observation for Epidemics of Vector-Borne Diseases. This activity is linked to the GEO work program, and especially with the activity of the community Earth Observations for Health. This activity deals with vector-borne infectious diseases, and all the activity is supported by the Copernicus program, the flagship program of the European Union in space, and also the Copernicus core services for atmospheric and services and climate change services, CAMS and C3S. Our action also pursues to collaborate with the EuroGeo SA project. This is the new project which has been launched in the framework of EuroGeo. So we are linked specifically to the Disaster Resilience Showcase, aiming to enhance societal resilience through timely and informed decision making. The action group engages organizations such as research organizations, academia, private sector, and decision makers. So far, more than 20 organizations are offering on a volunteer basis their data, skills, infrastructure, and scientific expertise, but several other decision-making organizations and users provide their support for co-designing and co-creation of the early warning solution an early warning solution which is applicable at the European Union level. So they are providing data, we are collecting data, harmonize the data, integrate long-standing previous efforts and developed capacities. And we, as a consortium, as a group, as an action group, we are creating innovation, and we validate the new tools and methodologies and models so as to derive the proper standards and the regulation in order to create a brand name, a solution which is under the brand name of the EuroGeo. Relevant research works has been conducted in the meantime. So we did all the, analysis, the review of the state of the art, of the science. We have been developing models relying either on dynamic and hybrid or physical modeling or data-driven modeling, using a long series of epidemiological and human cases data collected over the last 10 years in different countries of Europe. Here you see that we have already collected data from Greece, Italy, Serbia, Germany, France. These data are available. They are already on our system. They have been harmonized, cleaned, organized in a way that it can be used today for making analysis of the data, statistics, but also using the data for training and validation of the models, the forecasting modeling, actually. The motivation is obvious. Today, mosquito-borne diseases have affected almost 700 million people per year, and they are causing millions of deaths. The burden of mosquito-borne diseases is affecting disproportionately the poorest populations. And there are several factors, actually, that influence the seasonal and geographic distribution of vector populations and therefore the transmission of the pathogens. These factors are the continuous change of the climatic and ecological conditions, the global mobility of people, the way humans behave and how strictly they conform to the anticipated measures, the extent the urban sector and the environment is changing, and how rapidly the ecosystem changes and the ecosystem is disturbed because of natural disasters or human intervention, something that really at the same time affects the ecosystem services. Of course, as you know, these factors are monitored through the use of the Earth observation technology, either being space-based Earth observation data or in situ data or crowd data. This in turn justifies the need to move towards the proposed concept that is using these technologies for creating an operational, scalable, and interoperable early warning system. It has resulted, so far our activity has resulted in a fully automated early warning system that is validated on a seasonal basis with ground truth data, delivering to the national authorities and to the health organizations reports and forecasts for the mosquito abundance and the expected human cases. It is a generic system architecture. Later on, my colleagues will present you more in detail all this system architecture. But it is an architecture that it is applicable in any case of mosquito-borne diseases and seasonally related diseases, especially because it assimilates data and allows access to repositories of seasonal, environmental, meteorological, and ecosystem-related data, as well as allows access to the Earth observation satellite data in near real time. The system is scalable, so it can be easily scaled up and prove its operationality to more regions in Europe. It is transferable, it can be transferred, and it has been tested already in multiple geographical regions over Europe. It is using open data, open satellite data, and meteorological data, and environmental data. It builds up on the European technology. I mentioned already the Copernicus data, the Copernicus services, GEOS data, GEOS portal data, CAMS, CLS. It is provides automation. It's an automated data pipeline for ingestion of Earth observation data, together with epidemiological data and epidemiological data. It is a fully operational already. It has been tested operationally over Greece. I'll explain to you later on, and Italy, and it is now tested over other countries, Serbia, France, Germany. The innovation lies with the integration of multiple data sources, the use of open data standards and delivery of free and open products and tools, analyzes big data, and relies on advanced modeling and artificial intelligence techniques. It provides scalability and sustainability with many different aspects of that have a potential use in various sectors, not only in the epidemiology sector. It exploits the European investment in Earth observation and already ensures European coverage for the time being, but surely it can scale up to global level. And last but not least, as an action group, we paved the ground for the creation of a regulatory framework and the relevant work programs so as to understand how epidemiological and human case data could be collected in an harmonized way, how this data could be opened, shared, and analyzed for the benefit of a European early warning system. The impact is that we provide help to decision makers to improve health system responses, take preventive measures in order to mitigate the spread of mosquito-borne diseases. At the same time, we are addressing the relevant priorities of Sustainable Development Goals, very specific Sustainable Development Goals, number 3, good health and well-being, and adaptation to climate change, Sustainable Development Goal 13. As I mentioned already, 4 regions in Greece are receiving today the results of the implementation of the system. These are the regions of Central Macedonia, Thessaly, Crete, and Western Greece. For these specific areas, we have uploaded epidemiological and entomological data that have been collected for the last 10 years, some thousands of records of human cases year by year, as well as data from traps, mosquito traps, population of mosquitoes that are positive to West Nile virus. All this information is already there, uploaded, and available for analysis. And some ornithological data for the period 2009-2014. Also, again, data are collected with very specific coordinates where birds have been found, dead birds from West Nile virus. And so the system has been tested in Italy. It has been providing already data to the region of Veneto. Again, for this region, epidemiological and entomological data for the last decade are also integrated. And as I mentioned, the countries of Serbia, France, and Germany, the process is on progress. We're providing our results in the near future, but again, the data for the last 10 years are already available, integrated in the system, and we are using them for deriving analysis and modeling and assimilating the data. The models are advanced models. My colleagues will explain you better what types of models are used. Are hybrid, dynamic, and ensemble models, and data-driven models, which are providing predictions and forecasts of human outbreaks and mosquito populations and mosquito abundance at local level, municipality level, regional level, and which, of course, can be integrated at the country level. We have engaged several users already. The users are receiving our results in the form of reports on a systematic basis. These are monthly reports. We're receiving feedbacks from the users. The feedback of their users is used so as to fine-tune the system and validate our results. And at the same time, we have been establishing links with local and national health system. This is my presentation, and I would like to stop here. I think it's good that I give the floor to the next speakers, and I will give the floor to my colleague Elisabeth Parselia from the National Observatory of Athens. Elisabeth is going to speak about how to use the Earth observation satellite data in the development of this early warning system for mosquito-borne diseases. So I give the floor and the control of the presentation to Elisabeth. Elisabeth, the floor is yours.
Thank you, Harris. I would like to welcome you all in today's webinar regarding early warning system for epidemics using dynamic models, artificial intelligence, and space technology. My name is Elizabeth Parcelli, and I'm representing the National Observatory of Athens. And today I'm going to talk about the use of Earth observation data for epidemics of mosquito-borne diseases. I have a small delay. Okay, so how can satellite Earth observation data be exploited for tackling epidemics? Satellites can monitor environmental parameters that influence the transmission circle of mosquito-borne diseases between pathogenic agents, vectors, and intermediate hosts. What are the key advantages of using satellite data? Satellites have a frequent visit time and can acquire multiple images along the year. They can monitor and take acquisitions on a global scale. And nowadays, there are many satellite data which are totally open, offering to the users new opportunities for exploitation in new applications. So how did this all start? This team started with writing a scoping review paper, which focused on satellite Earth observation data in epidemiological modeling of 3 mosquito-borne diseases, namely malaria, dengue, and West Nile virus. The scope of this paper was to review the state of the art and identify research gaps. So the key findings were that researchers used various methods, models, and data, but they also used different metrics to measure the accuracy of their models. This made it very hard to compare the results. Therefore, it emphasized the need for common standardization methods and the need for developing early warning systems that can predict mosquito-borne disease outbreaks. So, based on the findings of the scoping review, we start designing and developing an early warning system that is using Earth observation data to forecast and monitor mosquito-borne diseases, focusing mainly on West Nile virus. The system has been designed to be scalable so that it can easily scale up and prove its operability to multiple regions, not only in Europe, but also globally. The system can be transferable. It can be easily transferred to other geographical regions with minor changes, and is using open data, which are open satellite and meteorological data, and is applying European technologies like Copernicus, GEOS, CAMS, CLS, etc. The system has been designed to be fully automated. Automated data pipelines for ingesting newly acquired Earth observation data get ingested into the database automatically. And the system has been fully operational for the last months and is under validation. The overview of the architecture of the system is presented in these slides. The system is using multi-source data. I'm mainly going to focus on the Earth observation data, whereas my colleagues are going to talk later in details in their presentations. So the Earth observation data were pre-processed and ingested into specific database that can manage and handle geospatial information. And later on, the results were visualized into WebGIS user interfaces, showing multiple results like risk maps, statistical graphs, and time series of environmental data. Here we can see the multi-source datasets and technology that have been used. We categorized the data into 3 main domains: the satellite and meteorological data, epidemiological and entomological data, and at the end, socioeconomic data. We can understand that managing all these kind of different sources that have different formats was a very challenging task. We used best technologies and database to store and manage all these different data sets. Open interfaces were used for data fusion, ensuring interoperability of the system. So, Earth observation data pre-processing and management. We had to face a huge challenge of processing more than 10 years time series satellite data coming from multiple sensors on the European scale in Greece, Italy, Serbia, France, and Germany, and manage all this EO data in the most efficient way. The solution, we chose the most up-to-date technologies and open source softwares. We use the Google Earth Engine, which is a cloud-based geospatial processing platform, which is totally open source and enables fast computation without any cost. Furthermore, we also use the Open Data Cube for geospatial data management and analysis of the system. The Open Data Cube streamlines the data distribution, organizes and analyzes large data collections coming from multi-sources. To leverage the information of all the underlying processing found in the multi-source datasets, we had to ensure temporal and spatial integrity of them. To do that, we extracted, transformed, cleansed, and loaded the data into a unified standard database that enabled to multiple users to have access to the most up-to-date products. The integrated big data have been utilized to perform data-driven modeling. Data-driven models rely on computational intelligence and machine learning. This was feasible due to the fact that we had a sustainable amount of data available and that the data have been continuous throughout the years. Just for the record, I would like to mention the numbers. We had close to 30,000 records of entomological data, close to 2,000 records of epidemiological data, and 20 terabytes of Earth observation data. The models have been applied and demonstrated in the Veneto region in Italy. The main goal of this data-driven model was to estimate the population of culex in the Veneto region. We had a rich data set of observations for the Veneto region, which helps us to validate the system. The models yielded promising results based on machine learning validation methods and have been also validated during the dataset of 2020 to ensure that the accuracies are met. The results are visualized into an intuitive and self-explanatory WebGIS platform. The platform enables to the users to see the risk maps and allows to authorized end users to insert the data. It also gives opportunity to show time series environmental data sets. So the next steps, of course, we want to apply the algorithms in other regions where we already have available data sets like Serbia, France, and Germany. We want to test the models to new vectors like Anopheles and Aedes in order to predict other mosquito-borne diseases. And we also want to make our model more robust. We want to apply multimodal in order to gain diversity. And at the end, and this is our ultimate goal, is to expand the model to epidemiological modeling and try to predict human cases. That's from my side. Any questions can be answered in the QA section. Thank you very much for your attention.
Thank you, Elizabeth. Thank you very much for the concise presentation. Now the floor is given to Professor Ioannis Koutsoukis from the University of Patras. Ioannis is going to give a talk about the spatiotemporal ensemble prediction system of West Nile virus dynamics. Ioannis, the floor is yours.
Thank you very much, Harris. I would like to welcome everybody. I'm Yannis Koutsoukis from University of Patras, and my talk will be about the spatiotemporal ensemble prediction system of West Nile virus dynamics. I would like to stop the video in order to avoid any delays. Okay. The Laboratory of Atmospheric Physics at the University of Patras is a small lab with three main research pillars. The first is weather and climate modeling, and using, in particular, predictive modeling of weather and climate, using approaches such as deterministic, probabilistic, and algorithms from complexity theory. In addition, we also model weather-dependent coupled systems, such as air pollution, epidemics, energy, and agriculture. One of them, the epidemic modeling, is the one that I'm presenting here today. The second research pillar is atmospheric monitoring. We have here infrastructure for solar radiation, clouds, aerosol, and stable isotopes, which are also used together with diagnostic models. The last pillar is climate reconstruction, in particular time series homogenization and geostatistics towards the development of high-resolution climate atlases. So this is a small introduction to our group here. Now I move to the problem. The core idea here is to model West Nile virus at the municipal level. Prior to the modeling, in this slide, we present the data facts at this scale. West Nile virus arrived in Greece in 2010. In the last decade, the number of years with West Nile virus human cases at the municipality level varies between 0 and 6, as you can see in the left chart. There are municipalities where West Nile virus never occurred, and there are municipalities where we had 6 years of cases in the last 10 years. Now, using tools from complexity theory in the right chart, we identify 2 huge West Nile virus hubs in Greece, one in central Macedonia and one around the capital city. In addition, there are 2 smaller hubs that are located, one in the region of Thessaly and another one in northeastern Greece. So, those are the data facts, and our model is to reproduce those charts. The model we have developed is a continuation of an earlier work where an in-depth sensitivity analysis of a model operating at the regional level identified the parameters that drive the model uncertainty, as well as the timing of their importance. This is the reference number 1 you can see below. In this work, that model has been downscaled at the municipal level and all its parameters have been recalibrated. It is a SAIR model where SAIR stands for susceptible, exposed, infected and recovered, which considers the West Nile virus circulation between mosquitoes, birds and humans. In the model, the populations are split into 14 health states. The transition between the 14 compartments is controlled by 25 parameters, which, as you can see in the left box, have environmental, epidemiological, entomological, geographical, or demographical dependence. In addition, there are also few parameters that are fixed. Now, what does this model predict? The model output consists of the population estimates at each compartment. For example, the larvae abundance, mosquito abundance, the infected mosquitoes, infected humans, etc., for all 14 compartments. In addition, there are many other indices which can be estimated as byproducts of our results, such as the R0, the basic reproduction number, which controls the disease strength, or several risk maps. Now, this is the model. Let's see what this model can achieve in historical simulations. The database, we trained the model in all the available data we had in Greece for the period 2010-2019. Now, following the downscaling of the model, some fixed model parameters have been estimated at each municipality. Then, the interannual simulations showed the capability of the model to identify the municipalities at risk on the basis, of course, of all the parameters which had environmental, epidemiological, or other dependence. The chart on the left, for example, shows for a typical year, namely 2012, the observed cases of observed human cases of West Nile virus in Greece. The chart on the right shows the modeled human cases for the same year at the municipality level. With green color, there are municipalities where we had between 10 and 20 cases, human cases. With the light blue, we had between 3 and 10 cases, and with the dark blue, we had between 1 and 3 cases. As you can see, the agreement between the model and the observation is very good. Of course, this is just 1 year pick out of the 10. What about all years together? We see here the skill of the model is here evaluated over all 10 years with the index called probability of detection, which shows what percentage of the observed cases are correctly captured by the model. In this chart, green color means probability, detection probability over 80%. The light blue color means, of course, 80%, over 80%. Consider that since the maximum number of years with cases is 6, green color can be either 83% probability or 100%. Means the model captured either all 6 years or 5 out of the 6 years. So it's, and as you can see, the majority of the municipalities are with a green color. Then there is the light blue color where the municipalities were correctly identified at risk for the with probability between 60 and 80%. And last, there are few municipalities where there is the detection probabilities on the order of 50%. Those are presented with the red color, the light red color. And last one, there is one municipality in yellow where detection probability is between 20 and 40. Actually, at that municipality, there were 3 years of cases and the model identified only 1 out of the 3 years. So this, in principle, is 33% probability. So validation statistics for in historical runs seems that are very well. The whole procedure is highly scalable as demonstrated from the application of the whole procedure to the datasets of the Veneto region in Italy. Here we can see results again for 2012 at the 581 municipalities of the Veneto region. For the Italians can clearly identify 2 urban municipalities. One is Padova and the other, I'm sorry, I don't remember the name, which are not where the model misses the cases, but for the majority of them, it is the identification is correct. Now, so far, we have seen results for historic periods. We trained the model. Now, let's move to see what are the challenges to make this work in predictive mode. 2 challenges exist in the operation of the model in forecast mode. The first one is the knowledge of the expected meteorological conditions for the coming months. The second is the knowledge of the initial epidemiological state. For both problems, for both challenges, an ensemble approach is adopted. For the first one, to tackle the meteorological uncertainty, we consider all 51 ensemble members of the seasonal forecast released each month from ECMWF. This is the easiest of the 2 problems. The second problem is tough. We must infer the initial epidemiological state given actually no field data, because virus circulation in spring is very hard to discover. Here we have developed a module which employs another ensemble technique based on analog past forecasts and observations. We have also tested several machine learning algorithms, and we ended up with this ensemble technique because it outscored all machine learning algorithms by at least 15%. Okay, I think I have time, so I can solve this also. In this chart, we start, we remove epidemiological uncertainty and consider only the meteorological uncertainty. What does it mean to remove epidemiological uncertainty? We assume that we have the best available epidemiological state, mean maximum 1 infected mosquito per municipality. So all the infected humans arise mainly from the variability of the meteorological conditions. You can see here that there are two municipalities. There are two, I think it's called the Municipality of Thermaikos and Thessaloniki, where we have a probability between 1 and 25% to have West Nile virus cases. This under the assumption that the ensemble prediction system of ECMWF is unbiased. Some tests against old data show that there exists a small bias in those ensemble forecast system. So if we add this bias in the results, we can see that a few more municipalities can arise, which are municipalities at risk mainly due to the weather uncertainty. Okay, now let's move to the most probable situation where we tackle also meteorological but also epidemiological uncertainty. There are 3 levels of information that is presented. First of all is the probability of occurrence. This, as I said before, comes, there is another ensemble module before which predicts, infers the initial epidemiological state. What does it give for the region of Central Macedonia? In red color, you can see the municipalities at risk, where out of the over 150 ensemble simulations, at least at 75% of them, there is probability of occurrence of West Nile virus human case. There is also at lower risk, there is the municipalities in purple, and last, the municipalities with risk below 50% are presented in green and yellow. So this is the first level of information, probability of occurrence. Second question is when? When do we expect this incidence? For those municipalities, also here you can see in various colors where we expect the incidence to arrive in July, August, or September. And the last level of information is how many human cases do we expect at each municipality. As you can see, there are municipalities where the average number of human cases for all the simulations where human cases exist are 1 presented with green color, 2 presented with yellow, 3 presented with purple, and over 4 presented in red color. Those maps, of course, should be read together with the probability of detection chart, which I presented at the beginning, because the model skill, as you remember, varies across municipalities. So in order to have a more global view of the forecast, we have to see both charts in parallel. The same procedure has been repeated for all other municipalities which participate in this initiative, namely the region of Thessaly, here probability of occurrence, month of incidence, as well as expected number of human cases. The third municipality is the region, the third region is the one of Western Greece, where there are here 2 municipalities and risk. And the last one, the region of Crete, is clean, nothing is predicted for Crete. Of course, in Crete, the database to train the model was very small, but so far the results show that there is no risk for West Nile virus there. Besides this information, there is also several other things that can be used. For example, we can use model predictions. Here is as you can see on the vertical axis, is the mosquito abundance predicted from the model. This one, which is a forecast, can be used together with the field data collected by Ecodev, and as well as ensemble techniques to downscale this approach from the mesoscale spatial scale, which operates at the municipal level, down to, for example, to the village scale. And of course, at the smaller temporal resolution. So I conclude here stating the model facts. The West Nile virus 2-dimensional model has been developed at the Laboratory of Atmospheric Physics. It operates spatially at the mesoscale, which is a municipality level, and temporally at the seasonal scale, that is 7-month ahead prediction with daily timestamp. It's a dynamic model nested in an ensemble framework to account for meteorological and epidemiological uncertainty. It's highly scalable. It has been developed and calibrated using Greek datasets and easily extended to account for Italian data. France, Serbia, and Germany will be included in the future. It provides all necessary information for West Nile virus control at the municipality level, such as probability of occurrence, estimated timing, and number of human cases. Further, it also yields information for mosquito control, such as mosquito abundance, which, coupled with field data and ensemble techniques, can yield mosquito abundance at some municipal levels, for example, village. This research is ongoing. There are several things that we plan to optimize in the future. So I would like here to stop and thank you very much for being there.
We thank you very much, Ioannis. Thank you for this interesting and concise presentation. And the last presentation of the day is given by our colleague Spyros Mourelatos from Ecodev SA. The title of the presentation is Data-Driven Modeling for West Nile Virus Mitigation. I give the floor to Spyros. Spyros, are you?
I'm here.
There? Okay. Let me give you the control of your presentation. Okay, I think
Okay.
you are able to start. Yes.
Thank you, Haris, and thank you all for being here together with us. I will talk to you about operational modeling, actually, data-driven modeling for WNV mitigation. And let's say the reason why we're focusing so much on WNV is that because it has become endemic in Greece after the outbreak in Central Macedonia in 2010. Now, I will present you actually Okay, so this is what I will present you. I will talk to you about the 3 components: larvae, adults, and the assessment of risk. I will talk to you about the data because we're talking about really valuable and very expensive data. The products that we have been producing for the last 3-4 years, actually, they're mostly, I will focus on the bad, on the bite, on the technology, on adults. And then I will last with some concluding remarks. Okay, I will first of all talk a little bit about control. I mean, integrated vector management. How is it being done in the USA, and how is being done in European Union and neighboring countries? So in USA, we have about 20 years of WNV and more than 50,000 confirmed cases of WNV. And there, the control is being done for the last century, I should say, for at least 100 years, by the mosquito abatement districts, actually 1,000 MADs, 1,000 mosquito abatement services within the municipalities, and thousands of small or bigger, or even very big pest control organizations. The estimated total budget is something about $2 billion per year. And the MADs have a long history and organized for integrated vector management. Now, in our case, in Europe, we have more than 10 years of WNV, more than 6,500 confirmed cases. But here the problem is that we're not organized for mosquito control, actually. The area-wide mosquito control projects are made mainly in Southern Europe. We are not more than 30 mosquito control organizations with a budget of about less than 80 million euros, so representing less than 5% of the budget compared to USA. There are reasons for this, but let's not talk about this. Now, in Europe, we have 5 vector-borne diseases. The 3, chikungunya, Zika, and dengue, are related to Aedes albopictus. Here in Greece, we had the last 10 years malaria and WNV cases. Actually, we had in red, you see in the map here, the cases of malaria, more than 100 cases of malaria in 12 different foci. And we had more than 1,200 WNV cases all over Greece. Now, there are 3 different data sources that we have been using for the creation of our models, platforms, and applications. Now, the first one is of open source, right? Is the Earth observations, is land use, land cover, topography, demographics. I would like to thank here already the NOA, National Observatory of Athens, for their help and support to get access to all these data. And then we have the processed data, right? That means these are data that are coming out of 2 research projects that we are running as eco-development, along with Aristotle University of Thessaloniki, and along with some partners from Germany. I will come back later. And of course, we have all these field data, larvae, adults, and pathogen circulation. I'll talk later. So we have exploited, and this, let's say, adventure, this joint adventure with NOAA and all the other partners gave us the opportunity to get back to analyze the past data for the creation of our models. So we have been working in 4 regions, actually exploiting data coming from 4 regions, especially Central Macedonia, but also Western Greece, Thessaly and Crete. Now, the forecast that we are running for the models are using 10 hydrometeorological variables in a resolution of 2 by 2 kilometers, or 5 for Central Macedonia, or 5 by 5 kilometers in the 3 other regions that are coming from one of the 2 research projects that we are running. Now, the scalability, the idea is to construct robust models for Central Macedonia, and then to try to expand this capacity and this modeling to the other 3, let's say, Greek regions, representing in total 40% of the Greek situation, and then try to make this kind of exercise for Italy, then Serbia. I like to remind that Greece, Italy, and Serbia are the top 3, let's say, countries in terms of human cases for West Nile virus, and France and Germany, they are threatened. So this is, well, we're talking about our clients. We will expand our endemicity to them. Now, we try to validate the outputs through continuous, of course, refinement and upgrading these basic predictive models. And of course, the idea is to continue all these, exercise and all this initiative for the next 3 years. And this we can achieve because we have already, let's say, contracts with these regions and our partners, especially the operationals, I mean, CABs from Germany and let's say, and the Ecodev from France, they are, let's say, intermunicipal or inter-county, interdepartmental agencies that are producing data. So I will pass on the next slide. We must wait a little bit. What's happening? I don't know why it doesn't work. So I'm trying to, okay. So these are the three models in red. It's the ball, it's the bar, it is the bag. So these are three machine learning models, I repeat, in red. So you have the larvae, the adults, and the assessment of risk. All these models are weekly predictions on very, let's say, high resolution. Actually, the ball larvae, we're talking about predictions for the abundance of larvae of three genera, the Aedes, Anopheles, and Culex. The adults is for in terms of villages, and the VAR assessment, it will be again in terms of villages. So in blue, you see this geodatabase with open source and processed data. In green, you see the field data, right? Mosquito larvae, or mosquito adults, or pathogen circulation. Next slide. Yeah. Okay. Okay, I just wanted to show you, but it doesn't mind, the two basic research projects that we've been running with Aristotle University of Thessaloniki and with our, let's say, colleagues from within the bilateral project with Germany, which are CABS and Berhard Nocht Institute, actually with Norbert Becker and Jonas Schmidt-Tanasit. And here I show you the field data that we are collecting through our monitoring networks. On larvae, we have 40,000 breeding sites. We do daily samplings. I'll show you a little bit on the next slide how we do it. So we have been digitizing this kind of observations for the last 3 years. So we have already 400,000 inspections. Now, concerning mosquito adults, with traps of CO2 traps in 60 to 130 sites, we have every 15 days for the last 10 years, and we have gathered something like 8,000 samples. Some of these samples are analyzed, you see here, so to get an idea on the pathogen circulation. So we have, say, 2,700 analyzed to get these infected mosquitoes. We have also very nice networks with sentinel chickens. So we're working in, depending on the year, within 50 or 130 villages in the last 2-3 years now. And we are collecting blood samples from chickens, actually. And this is a very nice, indication for the pathogen circulation. And of course, we have the human cases in collaboration with EOD, with the Greek CDC, whatever. And in this case, the advantage that we have is that because we are called to make mitigation actions, that means that we get the XZ coordinates, the exact coordinates. I'm asking Sandra if my time is okay, because I'm standing here with Sandra Gever, my alter ego, my scientific alter ego, with whom we're working for the last 10 years, especially after the WMV outbreak. So this is the electronic platform, the eBite software and application. So here we have, let's say, changed the mentality and the culture in our enterprise by forcing 80 guys. We gave them, tablets to digitize, to record data immediately, in an electronic form. So we're working in that with this, capacity in 40% of Greece, and we have 40,000 breeding sites. That is maps in the system for 40,000 breeding sites. And this year, 2020, we are thinking that we will produce more than 200,000 inspections That means, measurements, observations, control actions. That means something much more than 3 million values. So to make analytics, data analysis on this kind of results. Now, I will not talk about the ball, about the weekly provisions that we get, predictions that we get through this eBike platform, because this is, let's say, operational. This is for us, for operators. It's a huge tool. It's how to say? It's a very nice tool, and but it's again, it's for us, mostly for us. And I don't know anybody else to have, digitized, the larvae data at that scale. Now, let's pass on the bad. Bad, so it's BITE. It's the big data technology, for adults. That's how we baptize this kind of bad adults, because they're bad adults anyway. So here I show you just the Culex and the Aedes, not the Anopheles, because this is it's a work in progress. The most important in that these are, of course, the results that we take on key features based on machine learning analysis on the historical data for 10 years. The most important is that we have a big percentage in blue out of these key features that represent open source data, right? And this is interesting. That means that this kind of algorithms can be generalizable, can be transposable. Now in green you see the Ecodev data, and in pinky whatever, I mean, it's the the processed data. So theoretically that means that we're working on that just to have this kind of proportion, a bigger proportion in open source, either raw, either processed. So the fitting of the model, to be honest, sometimes it's this, for instance, what I show you is the 1/3 of the training subset from the data from Central Macedonia. So, and the second graph is a subset, a subset of this first set. And let's say that the fitting is quite, let's say, promising, more than promising. And the next slide is on yeah. So I have 2 minutes, right? Okay. So this is for Culex, the same image. Next. Now, this is Mosquito Vision. This is the application. I will not have the time to, let's say, to run it. What is most interesting here is that we provide 5-day predictions based on BAD. Of course, this application is on BAD. You can download it from, let's say, from, store. Yeah, from the Google Store, Play Store. Mosquito Vision, you just tap Mosquito Vision and you got it. So we have evening prediction, daily evening for 8:30 up to 10:30, which is related to Aedes. And then you have, predictions for night, which are for the time being related to Culex, but then will come also the Anopheles. I think that's the first at that scale. According to what I know, that's the first at that scale, application for daily. Daily predictions for, the feeling nuisance. The feeling nuisance is also, validated by 100 peers that are related, to this kind of exercise. And of course, to other people as well, about at least 300 presidents of the different villages, etc., etc. So, and also we do also calibration with recurrent neural network every two days. To be sure that the predicted abundances are close to the observed ones, so that we can transform this kind of abundances to the feeling, which is a very difficult exercise anyway. So I try to pass to the next slide, but okay. So this is finished up. We are finished up with the adults. And now I will tell you a little bit about the assessment of risk, because when you're running a mosquito control operation, you need decision criteria for the extra mitigation actions that you need to do against WNV. And for us, the extra is door-to-door. Why door-to-door? Because we know that when a village is, is how to say, is threatened by WNV, and this threat we can estimate through the, the high levels of pathogen circulation within or around this village. And believe me, we have a lot of villages, about 1,000 villages. Okay, Sandra, I'm finishing. And that means that we have to make decisions for the appropriate, right? For the appropriate door-to-door applications. Why door-to-door? Because in 300 out of these villages, for instance, we have cesspools. So that means that we have to go and to open these cesspools. We get to go door to door. So we know we need absolutely valid prognosis to do the appropriate door to door in order to reduce the incidence in WNV. And this is something that I'm waiting for, actually, this kind of equation to try to have the result of this kind of question. And the second thing is I'm waiting this kind of bar, assessment of risk. So concluding remarks, I will go very quickly. You can read if you like. So from the wait and see methodology that we had up to now, we must make a transition. And this transition is not only technological, sometimes it's cultural, and it's also managerial. And this tradition must lead us to a build and the scalable data systems. We must make decisions not only on our instinct, as we were doing, a couple of years ago, but we must establish rigid and very clear decision support systems. Now, I like this initiative because it forced us for the 6 months to digitize our data and our friends' data, and I will tell you who our friends are, and to try to to upload all this kind of information in a relationship, in a relational, kind of web platform. Now, I would like to thank just 30 seconds. I would like to thank our partners. Of course, Haris and Elizabeth for the drive and support from the National Observatory of Athens. I would like also to really thank all our friends especially from CAPS, Christophe Lagneau and Gregory Lambert, and from, AD Mediterranee, the French guys, Christophe Lagneau and Gregory Lambert, and of course, Norbert Becker and from CAPS, and Jonas Schmid-Anazit from Berghahn Nocht Institute, because they provided us with valuable data. We cleaned them, we digitized some of them. Actually, we thank you them. We will exploit them in the next, and perhaps in a couple of months, we could, why not organize a second webinar to present our progress in terms of, of our own models and by using the data of our friends. Also, I would like to thank Dusan Petric from Serbia, because he delivered us Serbia, and Anna Papa and Michael Dovas from the AUTH for the MIRs, the infected mosquitoes and the infected chickens, and Eleni Katragou, because in this project we have together, she is providing us with a lot of forecasts, a 5-day forecast on a resolution of 2x2. So thank you very much.
We thank you, Spiros. Thank you very much for this very good presentation. Now we continue with the QA part of our webinar. We have collected already several questions. Before going through the question, I would like to give the floor to Mr. Komartsi, who has raised his hand for some intervention. Mr. or Miss Komartsi, sorry, are you there? Hello? If you could unmute your microphone. Okay. Mr. Komartsi, are you there? Okay. Okay, maybe later on. I go through the questions. So we have collected already several questions. However, if you want to make your questions now, just feel free. I go one by one as they have been received. The first question is from Miss Angeliki Martin. I think it's a question for me. Can we join the consortium or organizations that give data on a voluntary basis? So the answer to this is that the action group for Earth observation for epidemics is open, of course, action group to evaluate new collaborations. The decision is coming by the GEO working group, and everything depends on the added value which is to be shared between partners. About the data, and the data are open, of course, all data that are coming from with open standards like Copernicus data, GEOS data, satellite Earth observation, derived proxies, etc. All these are free data. However, still the data like entomological data or epidemiological data, like they have been presented by partners, are still under the ownership of the organizations that collect data, analyze data. Still, there is no regulation for openness this data at European Union level anyway, but of course, for all other types of data that are already open and provided freely, I mean, the ones that are collected by the National Observatory of Athens, satellite imagery, proxies, meteorological data, etc. All these data which have been already available and analyzed, collected, analyzed, can be available. Of course, if there is something more to discuss, I'm here, I'm available, and we can discuss it offline. The next question comes from Mr. Wilfried Reinhold about the role of infected horses in the early warning model. Now, I think I give the floor to Ioannis to reply. I think it is a question to Ioannis. Ioannis, are you there? Yes.
Yes, I'm here.
I see you. Yes.
Well, the answer is that at this model version, horses are not included due to data scarcity. Driven by this limitation, the next population that we plan to include in our model is the ornithological population, because there are several records there. So the answer is no horses at this version.
Okay. Yes, Spiros, you want to intervene? Yes, please.
Integrate horses from Serbia, because Tamas Petrovic, the guy from the veterinary, Institute of Novi Sad in Vojvodina, Serbia, they have horses. They have a lot of horses. I mean, okay, there are difficulties with that, but we will try to integrate this as well. I mean.
Okay. Is Anna Maria Conte that wants to intervene on that question? I saw someone raising his hand or her hand for. Okay, no. Okay, we proceed. There is one more question for Mr. Kormarci. I think it's again for Ioannis. Ioannis, you mentioned about the municipalities in Macedonia that have been ranked on West Nile virus occurrence in 6 years. And the question is if this, if this ranking comes on human cases, by analyzing human cases, or circulations in sentinel chicken, horses, mosquitoes, or a combination of both. Could you elaborate your answer on that?
Yes, the answer for both questions is that the maps have been created from the observed cases of infected humans.
Okay.
Both maps.
On human cases. Okay, thank you. Thank you, Ioannis. Okay. And a question for Spiros. Spiros, you mentioned in your presentation the amount of money which is spent on mosquito control in Europe. Could you please repeat this, because some colleague is asking again on that? And
yes.
Actually, I missed it.
Well, my estimation is very rough. Okay, I know the price. I mean, the money that are spent a little bit in France, in Greece, in Serbia. I estimate about 80 million euros per year. And this includes, of course, not the research. Okay, this is the operational. I mean, the insecticides and especially the manpower. I mean, the enterprises. And we have about 30 mosquito control organizations in this game. More and more private actors. Now, it's very difficult to make any calculation for the PCOs. It's very, very complicated. So I'm talking about, let's say, the official, national, regional, or municipal, how to say, operations that I have in my knowledge. It's a very rough estimation.
Okay, thank you, Spiros. Are there any other questions from the attendees? If someone wants to speak or to intervene, just raise your hand. I don't see someone willing to. I see
Someone has raised a hand.
Yes, I see Mr. Komarchi, but I gave the floor before. Mr.
Yes.
Komarchi, are you there?
Yes, I'm Dushan. My computer name is Komarchi, which means mosquitoes.
Ah, okay, sorry, sorry, Dushan. Sorry, I now recognize you. I'm sorry.
Yes, yes. Sorry. Yes, I was wondering. I put this question to Yanis about how the hubs are defined, because we had also defined the hubs in the northern Serbia, but combining all the human cases, mosquito detection, mosquitoes, horses, and birds, and we also have well-defined hubs in Vojvodina. So it seems that this could be further investigated and improved by adding the sentinel chickens, what you have in Greece a lot, and mosquitoes and horses from some other regions, because we have also plenty of data on horses. And I think France, AD Montpellier has a lot of data on horses, supposedly. Yes. Thank you.
This is great. Yes, this is great. Thank you, Dusan. Yes, as you know, I mean, now we will continue with the Serbian data, and I'm sure that we will be able to exchange further and data and modeling or assimilating all this data into the prediction and forecasting of cases. I see Spiros raising his hand. Spiros, please.
Yeah. Okay. For our bar model, and I suppose also Yanis will do that. Perhaps everybody can do that. I mean, not the way Yanis does it, but okay, we are trying to become Yanis when we become older. But let's say that the pathogen circulation can be, taken into account by, of course, the horses, by the sentinels. I mean, the Serbians and the Greeks are the only ones that I know of, that have, for instance, chickens. Backyard chickens, which are, very, very interesting as an information, and of course the MIRs. So we did not have the time or the resources still to integrate in our small model, the bar model, this kind of pathogen circulation, in which we will integrate well demographics, and also we, with National Observatory of Athens, we have also the ages of the people every 10 years, and so on. And of course, the degree days, and of course, the mitigation actions, such as the door-to-door or whatever. So we have a lot of work in progress. So that's why I think that we must meet again in a couple of months or so.
Okay, thank you, Spiros. Any further questions? Please, feel free. Make your questions. Okay, if there are no other questions, I think I should close this session here. Of course, consider that whatever you'd like to know about all this action and all this activity in regard to the development of this early warning system, please feel free, come to us, make your questions, use our contact details. We will be very happy to exchange with you. We will be very happy also to exchange with user organizations, health organizations, organizations that are dealing with the control of mosquito-borne diseases. This is the right food for us, so that whatever we develop is adapting to the real, to the daily practice and the daily needs of your organizations. So let us know your feedback on what has been already developed and give us more insights on how to become better and how to become closer to your real needs. I see again, Dusan, yes, I think, Dusan, do you want to add something more?
Sorry, not to add, but to ask. Are you going to share the presentation with us or link for YouTube?
Yes, sure. Yes, we will share the presentations. The presentation will be uploaded on our website, and from there you can, of course, get the presentations.
Excellent.
And the webinar will be also uploaded. It has been recorded and will be available to all.
Thank you.
Okay. So once again, I thank you very much for your kind attendance, and I hope to keep in touch and exchange further, and we will inform you for the next series of webinars that we are going to give in the next months. Thank you very much.
Thank you, Haris.
Thank you all.
Thank you all.
Thank
Have
you,
a good day.
Elizabeth. Yes. Bye-bye.